Good morning, everybody. Hope you're all healthy and safe at home. So let us move on to the next section of Module 3, Section 17.4, Functions of Complex Variable. So to understand or to learn more about complex numbers and complex analysis, we'll be dealing with the functions of complex variable. So what is actually a function? Let's just revise what is it. We have learned in our earlier classes and all that a function from a set A to a set B is actually a rule that assigns to each element in A one and only one element in B. Okay, corresponding to every element in A, we must have a element in B. That is what a function is called. It is actually a rule. So for example, if f of x is equal to 2x, then for every x we can find a value, that is we have to multiply x by 2. So if B is the element in the set assigned to the element A in the set capital A by f, then we say that B is the image of A and write B is equal to f of A. These are just the notations. I'm just revising the things which you already know. If A is an element of A, capital A, and corresponding to that, if we have the element B in capital B such that B is equal to f of A, then we say that B is the image of A. Okay, small b. And what will be the set A called as capital A? It will be called as the domain of the function, and the capital B, that is the set of all images, will be called the range of the function. Okay, now if the function gives us real values like some root x or something, don't take the concept of root x. If we have some, say, a simple function, say f of x is equal to x plus 2. Okay, if x is real, then the corresponding x plus 2 will also be real. So such functions are usually, we are dealing with real valued functions. So they are functions of real variables. Now let's see what happens to the functions of complex variable. So there is nothing, pretty much the definitions and all, everything is same, but when the domain capital A in the definition of a function is actually a set of complex numbers, we say that f is a function of complex variable. Okay, that is f is acting on complex numbers. So we naturally call it as a function of complex variable or a complex function. So if we say that image w of a complex number z, again will be another complex number, say u plus iv. If z is x plus iy, then its image w will be some other complex number, say u plus iv. That is w is equal to f of z. Okay, and f of z, that is w, is u of x comma y plus I v of x comma y, where u and v are real valued functions. Okay, u and v are again another functions of x and y which are real valued. Now there is one thing that we need to note, as in case of real plane or real valued functions which can be drawn or graphed in a real plane, complex variables, functions of complex variables or complex functions cannot be drawn easily as a graph, because you can see that w is actually depending on u, v, x and y. So it consists of 4 dimensional coordinate system. So it will be very difficult to graph this complex functions, but we have methods to like plot the region and map them. So we shall just see some examples of some functions which are given in your textbooks. So these are a few of the examples of complex functions, like f of z is equal to z square minus 4z. F of z is z by z square plus 1. So but here you have to note that the denominator must not be 0. So in this case, in a real case, there is no possibility of this term to be 0, because this is square. So the square of any real number is again positive, and plus 1 is again a positive number, so it can never be 0. But in case of complex number, there is a possibility. Why? Because I square is nothing but minus 1, right? So this function is defined for all complex numbers except for z equal to I and z equal to minus I. So z should not be equal to I, nor it should be equal to minus I. Then the third function which is given as f of z is z plus real part of z. That is also true for, it holds for any complex number. So these are some of the functions. Now each of these functions can also be expressed in the form like we have done. We have seen w is equal to f of z is equal to u of xy plus iv of xy. You can express it how? They have just explained one example, that is f of z is equal to z square minus 4z. We just substitute the value of z in this expression, that is z is equal to x plus iy. So we'll have this is equal to x plus iy square minus 4 into x plus iy. Just expanding and combining the terms terms without I together and terms with I together, you will get it in the form u of xy plus I into v of xy. So that is simple. We just have to replace z by x plus iy. Now guys, just look into the figure 17.4.1. So we had stated that complex functions cannot be graphed easily, but we can map them, like there is a mapping from the z plane to the w plane. Okay, both are complex planes only. In z, x is the real axis and y forms the imaginary axis, and in case of w, u is the real axis and v forms the imaginary axis. So you can see that corresponding to any value in this domain of f, that is in this region, we find w. Okay, so we cannot graph a complex function, but we can map or transform a particular form. The function can be used to refer, or it can be interpreted as a transformation from the z plane to the w plane. So that is given in this particular example. That is we are asked to find the image of the real line z is equal to 1 under the mapping f of z is equal to z square. Okay, so just see figure 17.4.2. In the z plane we have a real part of z is equal to 1, that is x is equal to 1, right? So if z is equal to x plus iy, x is 1 and y can take any value, so it will be actually a straight line, x is equal to 1. Now the function is f of z is equal to z square. So what we are asked is, what will happen to this particular line in the z plane when this complex function is acting on it. Okay, so if f of z is equal to z square, we can simplify it, like substitute z is equal to x plus iy. So we get x plus iy whole square. So that will be nothing but x square minus minus y square plus 2xy I, right? So here we have u of xy will be nothing but x square plus y square, and v of xy will be 2xy because I will come there, right? X plus iy into x minus iy, right? So we'll get x square minus y square and as the real part and the imaginary part as 2x. Now if we substitute the value of x is equal to 1 in u of xy and v of xy, we get u is equal to 1 minus y square and v is equal to 2y. Now v is equal to 2y implies y will be v by 2. Y is v by 2. So we'll substitute this value in u, that is u is equal to 1 minus v square by 4. So we'll get a relation between u and v. Then only we can map in w plane, right? If we have a relation between x and y, that is x is equal to 1, there is nothing else. So to find the corresponding image, we use the function which is given to us and find a relation between u and v. Okay, so when x is equal to 1, we get u is 1 minus y square and we substitute the value of y is equal to v by 2. So we get u is equal to 1 minus v square by 4. So it is actually the part of a parabola which is shown in the figure. So the more about this thing will be dealing later in different chapter. So this is how we can find the image of any region in the z plane. What will be the image in the w plane? concept of limits and continuity and derivative and all are completely similar to that of our case in real numbers that we have done. There is one major difference. We shall look into that. So let's see the definition of the limit. That is, suppose a function f is defined in some neighborhood of z dot except possibly at z dot itself, then f is said to possess a limit at this point if and it is written as limit z tends to z dot f of z is equal to L. Here L is the limit. Now this is possible if for every epsilon greater than 0 we can find a delta greater than 0 such that modulus f of z minus L is less than epsilon whenever modulus z minus z dot is less than delta. Okay, I hope the concept is clear. That is, it is simple. That is, f of z and L will be values in the corresponding w plane, and z and z naught are points in the z plane. So when z comes close to z dot, okay, that is, as it comes close, their distance is less than delta, and delta is a very small quantity. So as z approaches to z dot, what should happen? F of z should also approach to L. Then we say that the limit of f of z is L. So z tending to z dot will give f of z tending to L. Okay, we shall give the definition of the continuity also, and then we'll move on to the difference which is there in the real case and the complex case. The second point is, a function f is continuous at a point z dot if limit z tends to z dot f of z is equal to f of z dot. That is, the limiting value should be actually the value at z dot. Okay, so a function f is continuous at a point z dot if limit z tends to z dot f of z is equal to f of z dot. Now this is another property of continuous functions. That is, if two functions f and g are continuous at a point z dot, then their sum and product are also continuous, and their quotient is continuous if and only if the denominator must not be 0. That is, g of z dot should not be equal to 0. So these are the definition of the limit and the definition of continuity. The limit should, in case of continuity, the limit should exist and it should be equal to the function value. And we have properties of our corresponding limits also. That is, if we have the limit of two functions, then their subproduct, if two functions are continuous, if their limit exists, then their sum as well as their product and everything will be also continuous. Now let's see what is the major difference that is there in our case of limits in the complex variables. So can you just look at the figure 17.4.5. that is, it states that you can see that z is approaching to z dot and correspondingly f of z approaches to L, but you can see that there are different paths. You can see the black line. The black lines depicts different paths or different ways. That is, in case of real numbers, we had discussed about the left hand limit and the right hand limit, right? So x tends to x dot from the right or x tends to x dot from the left. But this is not the case in complex. That is, z can approach to z dot from all possible manner. It can approach z dot in any direction. From any direction. It's not necessary from left and right. It can approach in any direction. Okay, so that's what you can read. The fundamental difference between the definition and limit concept in real variables lies in the understanding of z tends to z dot. That is, for a function of single real variable, limit x tends to x dot f of x equal to L means f of x approaches L as x approaches x dot either from the right of x dot or from the left of x dot on the number line. But since z and z dot are points in the complex plane, when we say that limit z tends to z dot f of z exists, we mean that f of z approaches L as the point z approaches z dot from any direction. So that is the important difference between limits in real case and limits in complex case. In real case, we are dealing that x tends to x dot either from the right or left, and corresponding to the function value approaches the limit. But in case of complex numbers, the possibility is that z can approach to z dot from any direction. Okay. Now this is theorem 17.4.1. This is the same properties that we know, that is if limit z tends to z dot f of z is L1 and limit z tends to z dot g of z is L2, then the sum will be L1 plus L2, product is L1 by L2, L1 into L2, and the quotient is L1 by L2, where L2 is not equal to 0. Then we had discussed the concept of continuity, that is a point is said to be continuous if the limit is equal to the corresponding function value at that particular point. So that was about limit and continuity. Next we shall discuss about the complex polynomial. We know what a polynomial is. Say 2x plus 3 is a polynomial, 5x plus 7x plus 8x square, and so on. I can go on. All those are polynomials. So what will be a polynomial in complex case? So let's see. A function f defined by f of z is equal to a n z raised to n plus a n minus 1 z raised to n minus 1 plus etc. a2 z square plus a1 z raised to 1 plus a dot, where a n is not equal to 0, where n is a non-negative integer and ai's are complex constants, is called a polynomial of degree n. Okay, same concept as that of real case, except that in real case the coefficients are real, and in complex case the coefficients are complex variables, right? Complex constants like 1 plus 2i and so on. So that is called a polynomial of degree n. Now polynomial functions are, as usual, they are continuous everywhere. Now we have a definition on rational function, that is f of z is equal to g of z by h of z, where g of z and h of z are polynomial functions in complex. Here this is existing, or this is continuous if h of z is not equal to 0, that is at those points. So this is both g and h are polynomials. So if you have to discuss the continuity of a rational function, we have to we'll be eliminating all the points at which h of z is 0, because at that points the function will not be continuous. So the functions, rational functions, are continuous except at those points at which h of z is 0. Okay, so next we shall move on to the concept of derivatives. That is, suppose the complex function f is defined in a neighborhood of a point z dot. The derivative of f at z dot is given by f dash of z, and it is equal to limit delta z tends to 0 f of z dot plus delta z minus f of z dot by delta z, provided this limit exists. So it is the same as in case of real, so there's nothing new about it. And again the same thing is applicable, that is f is differentiable at z dot, then it is continuous at z dot. So if it is differentiable, the function will be continuous also. So pretty much similar to the concept of real numbers, and we shall see some other rules of differentiation which is applicable, like for example we see the constant rule, the sum rule, the product rule, everything that we have done in the real case is applicable here also. That is, the derivative of a constant is 0, then d by dz c into f of z is equal to c into f dash of z, d by dz f of z plus g of z is equal to f dash of z plus g dash of z. Then the product rule, d by dz of f of z into g of z is equal to f of z into g dash of z plus g of z into f dash of z. Then d by dz of f of z by g of z is g of z into f dash of z minus f of z into g dash of z whole divided by g of z square. And the chain rule is also applicable here, that is d by dz of f of g of z is equal to f dash of g of z into g dash of z. So, and there is one more thing, that is a power rule, that is d by dz of z raised to n is nothing but n into z raised to n minus 1, where n is an integer. So these are the basic rules which we will be using to solve the problems and all if we are asked to find the derivative of a complex function. So this is pretty much the same that we have done in the case of real numbers or real functions. So let's just see an example which is given in your textbook. That is, we are asked to differentiate the function f of z is equal to 3z raised to 4 minus 5z cube plus 2z. It is pretty much simple. F dash of z would be equal to 3 into 4z cube minus 5 into 3z square plus 2. So that is 12z cube minus 15z square plus 2, right? And we have to differentiate f of z is equal to z square by 4z plus 1. So that will be 4z plus 1 into 2z minus z square into what will be derivative of 4z plus 1. Derivative of 1 is 0, derivative of 4z is 4. So 4 into z square divided by 4z plus 1 whole square. Okay, so this is pretty much simple. Now if we look at the definition of the different derivative for a complex function, this just like in case of limit, we had said that a z can approach z dot from any direction. We have to check whether this is true in case of complex, in the derivative case also. That is, in order for a complex function to be differentiable at a point z dot, this limit must approach the same complex number from any direction. Okay, so the differentiability, the condition for differentiability of a function is greater, or it has more power than in case of real variables. Okay, so I hope to make that understand, we shall be dealing another example. That is, when we are considering the limiting value, that limit will exist if it exists in case of all the possibilities, in case if z approaches from, or if there is a change in delta from any direction. It should not affect the limiting value. If it affects the limiting value, then we will not say that the function is differentiable. So let's look at the example 4 that is given. That is, we are asked to show that this function is nowhere differentiable and the function is x plus 4iy. Okay, now if f of z is x plus 4iy, we will have z, if z is x plus iy, then delta z is nothing but delta x plus I delta y. Okay, so let's see what will be f of z plus delta z minus f of z, that is the numerator, right? So f of z plus delta z would be, instead of x plus 4iy, we have to replace x by x plus delta x. I hope the concept is clear. Here if z was x plus x and x and y, if it is denoted by x and y, we have x plus 4iy. So instead of z, we have delta z. So delta z, the corresponding real part will be delta x and the imaginary part will be delta y. So f of z plus delta z minus f of z will be x plus delta x plus 4i into y plus delta y minus x minus 4iy. Okay, so when we simplify this, x and x gets cancelled and correspondingly 4iy gets cancelled. So we'll get it as delta x plus 4i delta y, right? So what will be the limit value? That is, f dash of z will be limit delta z tends to 0, f of z plus delta z minus f of z by delta z, that is nothing but limit delta z tends to 0. F of z plus delta z minus f of z is delta x plus 4i delta y. So the numerator is delta x plus 4i delta y and the denominator is delta z, that is delta x plus I delta y. Okay, now let's see. Now we have to apply the limit delta z tends to 0. Okay, now suppose delta z tends to 0 along a line which is parallel to the x-axis. In that case, delta y is 0, right? So what will be the value? Delta y is 0 means delta x by delta, this term will become 0, this term will become 0. So we'll get the limiting value to be 1, right? And suppose our delta z tends to 0 along a line which is parallel to the y-axis. What will happen? Delta x will be 0 because there is no change in x. because the line is parallel to y-axis. So in that case, delta x and delta x becomes 0, and the remaining terms will get cancelled and we'll get the limit to be 4. So in one case, that is if we approach or if we tend delta z to be 0 along a line parallel to the x-axis, we'll get one value of the limit, and when we are approaching it along a line parallel to the y-axis, we are getting another value. So that must not happen for the derivative to exist. The limit must be unique, limit must be a particular single value. So in this case, when we are approaching the point in different directions, we are getting different values. So this function is said to be nowhere differentiable. So I hope that concept is clear to you. If you are just asked to find the derivative, we can easily do it by using the different rules which are given to us. And there may be cases where we have to verify that the function is nowhere differentiable, and in such cases we have to use a limiting formula, and we just have to determine the numerator and see that if it approaches. Mostly we will be using these two conditions only, that is one way, that is delta z tends to 0 along a line parallel to x-axis. In that case the delta y will be 0, and in the other case delta x will be 0. That will make our calculations much easier. So we'll just see the examples in such a manner. Now the next is so as we have this concept that the derivatives may or may not exist, we are moving on to a new definition, that is about the analytic functions. Okay, so what is meant by analytic function? A complex function w equal to f of z is said to be analytic at a point z dot if f is differentiable at z dot and at every point in some neighborhood of z dot. Okay, the function should be differentiable not only at that point but also in the neighborhood of z dot. Okay, so a function is analytic in a domain if it is analytic at every point in D. That is a simple definition, that's just a generalization. Okay, so if you see this differentiability is based on a point, okay, but analyticity is based on the neighborhood. It is a neighborhood property. Okay, it is not actually the focusing on a particular point or limit value at that particular point. Okay, so a function is set, and this comes in case of only complex functions. So a complex function is said to be analytic at a point if that function is differentiable at a point, at that particular point, and also in some neighborhood of that point. Okay, and there is another definition, that is the definition of an entire function, and is a function which is analytic at every point is said to be an entire function. Okay, a function which is analytic at every point in the complex plane is said to be analytic. Now we can easily guess an example of analytic function, that is clearly a polynomial function. Okay, a polynomial function will be differentiable at any point, it will be analytic at any point. So a polynomial function is clearly an example of an entire function. So these are the few topics that we have discussed right now, that is what is a complex function, and we discussed about polynomial functions with complex variables, constants as coefficients, and we discussed the limit and continuity and differentiability. All are similar, pretty much similar to the case of the real valued function. The only difference is that in real case we approach the limit from the left or right, but that is not the case in case of complex functions. We can approach the point from any direction. So while the differentiability condition rule is much stronger than the real case. So that's it, we shall wind up today's session. So everybody, thank you so much, stay home and stay safe.